Okay, welcome everyone to my continuation of what are my favorite theorems. Very biased collection. What else could favorite theorems be, right? Favorite theorems, a very biased collection. I would like to come back to something I actually talked about before, but I will try to explain it differently and add a bit more information because I just recently learned more about it, which is always exciting. You always keep on learning. That's wonderful. And what I will do is kind of a very nice kind of mixture between topology and graph theory, which I hope you will like. And it's what people call intrinsically linked graphs. Goes back to the 1980s, I think, as a definition, and we'll see what it is. And I really feel like this is a very surprising, the result of the theorem is like very surprising. So at least for me. And then I was like, I tested that on several people, just explained the problem and made them guess whether they think this is actually doable or not. And it's kind of a little bit, some people really guessed what's going on, some people weren't able to guess what's going on. So, well, whatever, give me your opinion, whether you think this is really, well, it's certainly a difficult problem and an easy solution, but whether it's as really surprising as I think, or maybe it's not as surprising, I don't know, I can't tell, but let's just jump right into it. I personally find it kind of the result, in the end, very surprising. Okay, so the starting point is a famous theorem, which is sometimes just called Kuratowski theorem, but actually the part I'm interested in goes back to Wagner, and so I call it Kuratowski-Wagner theorem, or just Wagner theorem, depends a bit. And essentially all you need to know about this is the following. There's a certain type of graphs, which are called planar, and this is really just, they can be drawn in the plane without intersection. So here's a planar graph. I can draw it in the plane without intersection. And drawing it in the plane without intersection doesn't mean that I can not draw it with intersection. I can clearly draw this one with intersection. Probably missing this edge here. But there's just saying there's some drawing without intersection. And an open problem, well, an open problem for some time, but certainly not nowadays anymore, is whether you can kind of check nicely whether a graph is planar or not. Because the subtlety is, in principle, you would need to check all embeddings and check whether it's planar or not. That's a bit annoying, but there's a better way of doing it. Right? Checking all embeddings is like checking an infinite set. That's a bit annoying, you know. Doing infinite things is quite an annoying task, but here's a better way of doing it. There is this graph that is called K5, the complete graph on 5 vertices, which is really just the pentagon graph. Where you just complete means you connect everything to everything, yeah, and you just connect everything to everything. I hope I haven't forgotten anything. Anyway, doesn't matter. So complete graph K5, you connect everything to everything, and there's a complete graph K33, which just means you have 2 sets and you connect everything to everything, but just in this bicolored version. So maybe what I really should do is I should go give those guys the blue color. That's a bit blue color. So blue colored vertices, red colored vertices, and you collect all blue and all red. And the point of the theorem is that these 2 graphs are the witnesses for planarity testing. So if you find one of them as a minor, if you know what a minor is, if not, forget it. If you find one of them, you are for sure certain that they are not planar, and if you don't find one, then you're for sure certain that they are planar. In particular, this property of recognizing planarity testing, so planarity testing whether a graph is planar, has a really nice algorithm, and even the slowest possible that comes out from this minor idea runs not that slowly. So it's actually pretty good. You can do better, by the way, but it doesn't matter for this video. So you can do it in ON3, which is kind of a surprising result, because a priori you would need to check all planar embeddings, or all ways to withdraw your graph, which is like not happening, which is really just not happening. But it's much easier to just check for 2 witnesses, and you can do that pretty quickly. Okay, so that was well known for a long time, maybe the 1930s or something. It was before. People have worked on this as well. And then later, there comes a different question. So, okay, whether a graph is planar or not is an interesting question. Whether I can draw it in the plane without intersection, whether I can do that same in 3 space, like in our space here around us, is actually a boring question, because you can always do it. In fact, every graph can be embedded in R3. In other words, you can always draw a graph in R3 without intersections. So that's kind of the boring question. So the real question is, can you do it without knotting? Right? So here's a knotting of K6. So knotting just means now things go over and under because it's somewhere in 3 space. So can you draw a graph without knotting? What does that even mean? Maybe there are graphs that are always knotted. It's kind of the same as planar. Just an analogy to planar, but now in higher dimension, 1 dimension higher. And the question of intersection boils down to the question of, can you do it without knotting? And to me, this sounds like a really difficult question. If you keep in mind how difficult knot theory is, for example, it sounds like really difficult, and I'm pretty stunned that you can say something about it. First, is there actually any graph that needs to be knotted, or can you always find the knotting, an embedding that is not knotted? Pretty strange, pretty difficult questions you could ask here already. Let me convince you that there are graphs that are intrinsically linked or knotted, whatever you want to call it. They're usually called intrinsically linked because you have a link. You'll see it in a second. Or actually, you already see it on the slide. Anyway, I will explain it in a second. But anyway, so intrinsically linked means every embedding contains a non-trivial link. So no matter what you do, it will be knotted. No matter what you do, it will be knotted. There's no choice. And this is something like the analog of non-planar graphs. Okay. Is there any way, are there actually graphs that are intrinsically linked or not? It's already a non-trivial question. But here's a nice slick proof in quotation marks, obviously. So you need to work out the details, but it's still comes close to a proof that K1331 is intrinsically linked. K311 is a graph here. It's K33 on the bottom, and then there's an apex vertex. That's why it's called K311. And the apex vertex is connected to everything else. Okay, and I claim that this is intrinsically linked if and only if K33 is not planar, and we indeed know was one of the witnesses, remember, that K33 is not planar. And the way to see that is the following. So imagine that your link sits somewhere in R3, and you arrange it in some form that the K33 sits in the plane. So here this bottom part now sits in the plane. Since it's not planar, there must be some intersecting edges that you need to pull away a little bit. So there must be some over and under crossing thingies, like in the picture here, right? It's not planar, so you can't avoid, no matter what you do, you can't avoid that. And you just use that because you now have some crossing, and you just use the one crossing to kind of generate a triangle that connects to the apex vertex, and whatever you can do to connect the other one, and you will generate a non-trivial link. Hopefully it makes sense, right? So you're using that K33 is not planar, you will find a crossing somewhere. You need a crossing somewhere in that plane. Use that crossing to generate something that goes through the apex vertex and something that is linked to that thing, and you will see that you will always find a non-trivial link in this picture. So, by the way, just as a reminder, a link is just a multi-component knot. That's why it's called intrinsically linked. You usually find those guys in the picture, right? Where you have your fingers and you can't pull them apart. Okay, I think this is a pretty nice, cool proof in quotation marks again that there actually exist non-intrinsically linked things. But can you go further? That's not so clear, right? And here comes what I think is a really surprising theorem, and it comes close to, it really is a Kuratowski-Wagner theorem, the one we had before, but now, this one here, but now for this intrinsically linked thing, because there are actually 7 witnesses. It's not 2 like in the previous case, and the graphs are a bit more complicated. It's called the Petersen family. But anyway, there are only 7 witnesses. In particular, you can test that in a machine in a very quick time. It's just, again, O of n3, where n is the number of vertices. And I don't even know whether this is kind of optimal. You probably can do better, but I haven't checked. But I think this is a really surprising theorem. So you can check this intrinsically knottedness, intrinsically linkedness of graphs really easily. It's not much more difficult than planarity. But I would have just naively guessed that it's much more difficult than planarity because we go a dimension higher. No, it's not much more difficult. It's 2 versus 7 much more difficult in that sense, right? 2 witnesses versus 7 witnesses. But here we go. I think this is a very surprising theorem. Some people say it's actually not surprising. I don't know, but I leave the conclusion to you. And what you can do is actually a little bit more. So when you play around with this intrinsically linked, it's actually not so trivial to find the first example. I showed you one, but to come up with that yourself is certainly a bit tricky, but it's kind of, again, a strange thing here, because essentially all examples are intrinsically linked. So what happens here is you can show that a random graph is intrinsically linked because a random graph has a lot of edges, right? And if you think of something with a lot of edges, then there are a lot of possibilities to form non-trivial links. So they should be somewhat intrinsically linked. And indeed, you can make a theorem in the usual probability way of probability 1. So if you throw all graphs in a big bag, you kind of scramble it through, you draw out one, probability is 1 that your graph will be intrinsically linked, which I find is kind of a nice statement in its own right. Anyway, I hope you enjoyed this video, and I also hope to see you next time.